I speak none of the other languages of South Africa, I'm sorry, but welcome, maybe? Yeah.
Bulgaria.
Sorry?
Bulgaria.
Bulgaria? I don't speak it. I'm sorry, I don't. But welcome. Yes?
Thank you.
Canada? I'm sorry. I'm sorry, Canadian. I speak Canadian. I do the French too, but that's less respectful. Anywhere else? What else we got up there? Sorry? Barcelona? Barcelona, wow. I'm going to be careful with that because there's a whole Spanish Catalan thing. But bienvenidos, bienvenidos. California. Okay, I've got my. As I say, welcome, and let's crack on. So, mysteries of matter. What is matter? Not what's the matter. I'm not that character from that Disney movie, but two people. Mysteries of matter. What is matter? Any ideas? Suggestions? What constitutes matter? What is? There's no. I mean, there are wrong answers, but we don't care. Anything. Matter? Yes. Up here. Ooh, I like that answer. Matter can be anything that takes up space. I'm done, let's go home. Yes, exactly. It's like stuff, right? Tables, people, stars, the air around us. We can't necessarily see it, but through different ways we can detect it, and that's a whole other show. Before I get launched into demos and things, a couple of points about safety. You might have noticed I've put some glasses on. If you hear an alarm or there's a sudden loss in cabin pressure, oxygen no, that's my weekend job. No, but if we do have to evacuate, we will use the exits through which you came at the top of the room if they're available. If not, left and right. I thought you could do that other job, didn't I? We're not anticipating any drills or anything, so if there is an alarm, treat it seriously, leave your stuff behind and exit calmly through those gates, and then it's all signposted for where to gather after that. And we will get to the next slide in a moment. Enough talking, let's see some stuff. Oh yes, for those of you in the front row, this is not like an aquarium show where you will get wet, okay? You'll see why in a minute. But do please stay in your seats. This is, I'm interacting with you like with words and questions and stuff, but there's no need for anyone to come up here, okay? Children, keep an eye on your parents, because they're very excited. I'm going to get my gloves out right here, and we are going to have a look at my friend, liquid nitrogen. At least one of those words should be familiar to most of you, and perhaps the other as well. Liquid nitrogen, I will first demonstrate to you that it is in fact a liquid. You're going to have to take my word for it that it's nitrogen. Already that. It's a liquid, and therefore we can pour it. A liquid is one of the examples of the states of matter, of course. Any other states of matter that we know? Just shout them out.
Gas.
Gas, solid.
Plasma.
Plasma, spoilers. There we go. But if we see here, ooh, I have the best job at CERN today because this is really cool. And I mean that literally. Anyone know the temperature of liquid nitrogen?
Negative 272.
In what units of that?
Celsius.
Celsius, we like that. What was the number?
272.
272 minus 272. That's just under absolute zero, so not quite, but it's a very good guess. Anyone else?
Minus 200.
Minus 200, more or less, yeah. Minus 196. Minus 196, so quite a bit cooler than outside right now. Will that do? A little bit more than that. And as we can see, I can pour the nitrogen from one container to another because it's a liquid. What state is nitrogen normally found at? Gas. It's normally a gas. You guys already know it. It's great. Okay, we've got a small enough volume now so I can take the gloves off, but I'll keep the glasses. And this is a very visual show, but for a second now, we're going to go to audio mode. I believe this is switched on. Yes. Yes. That noise is the liquid nitrogen boiling. So just like you're trying to make, anyone from Italy here? Daria? No? Okay, so I go into the accent. If you're cooking spaghetti, that's it, sorry. We will boil water to cook the spaghetti, right? So the water that comes out of your tap or faucet is a liquid, and then you heat it up, and it becomes a gas, right? It evaporates. And partly that hot water is going to cook the pasta. The liquid nitrogen in here starts at 196 degrees below 0 Celsius. And in the room right now, it's like 20 something. Right? Which is much nicer than the 35 we have outside. In Fahrenheit, it's a bunch of different numbers. That's your point. And so as it hits the temperature of the air above it, okay, it is becoming a gas. So if I were to walk away and leave this alone for a while, this liquid nitrogen would eventually just become gaseous nitrogen in the atmosphere around us. The atmosphere around us, in fact, is about 80% nitrogen. About 19% oxygen, and a slowly but ever increasing proportion of a bunch of other stuff. But yeah, 80% nitrogen is our headline statistic for the air around us. And that means that if we were to, wait, I'm getting ahead of myself, sorry. So I've demonstrated in a sort that this is cold, but let's see some like real effects of making stuff cold. And don't worry, if this seems a little bit like every day to begin with, the show crescendos, okay? We're not doing the big stuff right at the start. So I'm going to pour out some normal water right next to my laptop. Do try this at home. Up and out. So if I pour out some, no, I'm not doing that there. I'm going to do that here. Pour out. This is just water. Okay, this is the temperature of the room. It's just a bunch of water. There we go. And then if I pour my liquid nitrogen on top, you might have seen a bit of an effect earlier already. Is that going to be a good place to put it for that camera? Let's find out. We're going to pour some liquid nitrogen in. Correct response. The back, I'm not hearing you. So what do we have here? This is water vapor from the air, the moisture in the air, just like on a cold day, Canada. California, you can ask Canada about cold days later. On a cold day, you can pretend to be a dragon. Now this, of course, is not smoke. There is no fire here, right? This is the water vapor in the air cooling down rapidly and forming this sort of cloud, okay? And again, we can listen, and it sounds even more like boiling like that. And also, like, thanks in advance and all the way through for our supporting the technical booth at the top right there. They do a very good job every day. And I'm also doing this for, sorry, they watch this show twice a day all year, so they know what's coming. But yeah, they're really top guys. So I think we should give it now. I forget the wooden spoon. You can hear the ice forming. The water that was liquid has cooled down thanks to our liquid nitrogen, and now. Oh, I didn't do that enough. Let's get some more. Let's be more aggressive with this, huh? Oh, I feel like some kind of like witch. 3 people have seen Fantasia. Hey. Yeah, Shakespeare. I am British, if you couldn't tell. So here we go, I'm getting some ice. So I'm not going to be able to fish it out just now because it's too cold, but we do have some solid ice forming at the top of there because it is just getting so cold. So as we can see, when we have a liquid and we cool it down, it becomes. So ice in the case of water, that's right, but this is generally true. Okay? We're very familiar with water in our everyday lives, right? Because, well, it's so essential to life, right? And we know it in the forms of ice, liquid water, and vapor, right? But that's true of water. If you change its temperature, it changes state. That's true of basically everything. I'll bring up a slide just with a little demonstration of that. And I've actually formed this in a little triangle form. Solids turn liquid when they warm up, and then liquids turn to gas when they warm up. You don't have to go via liquid. Under the correct temperature and pressure conditions, you can skip liquid altogether, and solids can sublimate, is the word, into gas. That's true of solid carbon dioxide, for example. at kind of ambient temperatures. There is a word for gas straight into solid. Reverse sublimation, yeah, if we're not being creative, but they might.
Deposition.
Deposition, okay, I'll take your word for it. Right, literally your word, well done. At the end of the day, the words are labels for things. What we're interested in what happens. But yes, well done. And yes, to give you a sort of sense of scale of things, see if you can spot the slight error on this slide. Summer day at 27. See the note before about increasing proportions of other gases in the atmosphere. And so liquid nitrogen is up there at 196 below freezing centigrade. The coldest possible temperature is minus 273, so we were pretty close with our guess of 272 earlier. Superfluid helium, which we use in the Large Hadron Collider, which is the big accelerator that we use here at Cern to study all this stuff in way more detail, is at minus 271. So I believe there's a physics experiment somewhere else on Earth that goes between 271 and 273, so this isn't the coldest place in the universe, but it's quite close. Yeah. And so, let's see if my solid ice has formed yet. If I want to spoon that. How are we looking? Oh yeah, I've got a lump. I've got a lump of ice. I'm not going to be able to fish it out. So the vapor is actually preventing me from seeing what I'm doing. So I'm going to feed it from this bit. Here we go. Da, da, da. Hey. And just so for verification purposes, without touching this because it's really cold, but you can kind of just notice that that is in fact solid ice, right? So this is our water that has turned into a solid. Great. Yo, you went to Cern, man, so cool. What did you see? Well, there was this great exhibition, we did a tour, but this show, like, we kind of just throw some water. What? Crescendo. Water turns to solid. We're just kind of going over the basics and building up here. So water turns to solid. What about liquids into gas? Let's do that one next. Just like a liquid can become a solid when we cool it down, if we were to heat it up, I know I gave the pasta example just before, but if we were to heat up a liquid, it would therefore become a gas. So if I put this around here, I guess we'll be able to pick it up on the camera over there for a moment. Back there, and I'm going to pour what you will see is a very small amount of liquid nitrogen into my little bottle here. Okay. Precise aiming, precise aiming. Oh, I'm not worried about that at all. That actually just looks cool. Lively frost effect. Okay, got some in there? Yeah, not too bad. So we can see some water vapor cooling down above our bottle here, because what's going on? Well, our liquid is becoming a gas. And if I try to seal this off, we might, in fact, go to the spot. What's happening here? So the liquid is becoming a gas, and what is happening to its volume? Expands, it increases. It increases, but it's got to go somewhere, right? So it can't. The weakest point of the bottle is the tap. Ooh. Part of why it looks so good right now is that light, which is where I'm catching this out of. So let's see if I can do it. Oh, is it going to go? Is it going to go? Eventually, this stops. You see, it's not going up as high. Now, we're not controlling very well for how hard I'm pushing this in here. If I really go for it, let's see. And the point is that that small amount of liquid, that small amount of liquid is creating a very large amount of gas. That's what I want you to remember from this, okay? Not only is the volume increasing, it's still increasing. Yeah, I've got like one clap there. That wasn't that sarcastic, I can keep doing this for a while. All right, don't overdo it, California. I am still British after all, I've got to have some humility. Oh, hey. All right, we get the point. Occasionally we do this and we kind of close it out of reflex because the other one's closed, and then 2 minutes later. So I'm going to put that down there. Safety. We don't want it landing in here, do we? So gases and liquids have different volumes, how much space they take up, depending on their state, liquid or gas, which depends on the temperature, of course. So we've seen a liquid becoming a gas. Can we do the opposite? I'm going to like grab some gas and... No. I need some technology. Oh yeah, some technology in the show, finally. Aha! I know I said I'm a flight attendant, but I'm actually a clown. On the weekends, I'm mainly a dad. Because I know I'm tying on one. So my wonderful pump technology there has helped me trap some gas. That's all the balloon is, gas, in a tube made of rubber. Okay. And this tube at room temperature, pretty flexible. Like that's how they develop stuff. Okay. So we have air from the room trapped inside this rubber. Let's see what happens if we cool it down. And remember what we said about air before and its temperature. And its composition, sorry. The composition of air, what is in air, we remember is mostly nitrogen. Oh, we have some ear covering going on. That was a prediction. That was an interesting prediction. I could have asked you all what do you think is going to happen. I'm kind of taking it for granted that you're all curious about what's about to happen. And you can't see through the bottom of the table there because it's like nicely covered in our black tarp. But you could accuse me of like having some kind of trick point on the table there where this balloon is just going underneath. I said you could accuse me. It never occurred to me. But a child once in the front row was like, yes, it's going under the table. It's like a magic trick. No such thing as magic, kids. Just physics. That's all I want you to remember from today. Now, also the physics is kind of cool. But as you can see, no trick table. So where did the balloon go? The balloon was like that long, and it's in this tube, so that's longer than that. How's that, right? Is this like a Doctor Who TARDIS thing going on? No. The balloon is all still there. And so is the gas that was inside. It's just that, of course, because it's nitrogen, and we've put it in other nitrogen at the relevant temperature of minus 196, it has become liquid, and therefore, just like the liquid takes up more space as a gas, so the gas takes up less space as a liquid. And therefore, because the balloon is pushing on that liquid, it gets all shrinky small. But this is, of course, reversible. Just like my ice water is melting to become liquid again, so the liquid air that we just made is becoming a gas again as it meets the lovely room temperature outside here. Look at that, growing again. Yeah. Cool. So, liquid, gas, liquid. Fine. Other states of matter, anyone? We mentioned plasma, that's for later. What are we missing? Solid. Gas, yeah, solid. Very good. He said, waving a solid. Wood is a solid. People are more or less solid. There's a bunch of liquid in there, of course. Yeah, and we've returned to the original length of the balloon. This is, of course, repeatable, and I could keep doing this all day. Ooh, is that going to burst? How many burst? Let's see. The balloon is a solid. Okay, so the solid itself became slightly less elastic, of course. And we can see a more extreme version of this. So, I have here, let's go to Canada. Uh-oh. Don't you say. You're the excited bean. Okay. just pull on that, see what happens. No, right. What's this made of? Rubber, okay? It's just a rubber tube. Oh my God, what is Cern? Like, rubber tube. Even Canadians, they're not even polite about. Rubber tube, whatever, right? Rubber is a solid. It's a slightly special solid because when our young volunteer there pulls on it, it kind of stretches a little bit. I can twist it, whatever. I can smash it with a hammer. Okay. 12-year-old me is like, whoa. Like, I would be doing this even if you would. And we can smack the hammer. Makes a bunch of noise, comes to the table. Hammer just kind of bounces off because we have a bit of elasticity, okay? But But you know what I'm going to do now, right? I'm going to dunk it in liquid nitrogen, see what happens. And I want you all to be thinking to yourself, what's going to happen to the solid when we get it cold? Because remember that scale, right? We had warm things were gas, slightly colder things were liquid, even colder things were solid, and then what happens if solid gets colder? Does it get more solid? Let's find out. You can hear our boiling again. This really is, I think, spaghetti. One spaghetti. So, right? Those things. Oh. What made that noise before? This head doesn't make that noise. I feel like a tiny steel pan drum in there. There's a whole band, the Cheerio Curacao in the World Cup. My modern references. I know soccer. Sorry, football. All right, America. Okay. Oh. Well, it didn't get any smaller. I think it's kind of the same size, but bring out the 12-year-old. If any of this lands down here, we're going to leave it there, okay? Keep an eye on pairs. Cool. That's quite different. Keep going off there. Woo! Nice. You don't do this too much because, budget cuts. We can't be. That's half a joke. The CERN budget is only about 1 billion Swiss francs a year. Look at the number of flags we have outside. It equates to about 1 cup of coffee per taxpayer in those countries per year. So it's pretty efficient for everything we managed to do. Anyway, parenthesis over. Yeah, so this is cold, but it's warming up rapidly. It's still kind of hard, right? And then eventually, we'll see that it has come back to its already, even after just a few seconds, these end bits, I can already twist them. Okay? Let's see, yeah. So this elasticity was lost because we were smashing it with a hammer and it was breaking, unlike before. But it returns, okay? These processes are reversible. It's not perfect. There are losses, right? If I were to do this enough times, eventually it wouldn't be elastic again, okay? There are imperfections in these reversibilities. But that is the general principle. So, gases become liquids, liquids become gases, liquids become solids, solids change their elasticity. I don't want to say become more solid, that's not correct, but the properties can change with temperature, okay? Now, I want to talk about some slightly different solids now. I'm going to go and talk about magnets in a moment, but before that, a solid that is not elastic at all in the first place, right? With a rubber tube, we have that elasticity to play with. Here I've just got a big lump of metal on a chain, and at room temperature, whoop-de-dee, it goes through the little ring here. Okay, let's cool this down. Okay, more boiling. Right, hypotheses. What's going to happen if I try to put the ring around the metal sphere once the whole system is a lot cold? Yes, Karen?
It wouldn't fit.
It won't fit. Why is that? As the ring gets colder, it'll shrink. Well, let's have a look. Give it a few more seconds. Okay. Oh, that's long enough. Indeed. Not visibly, right? That looks the same, right? You might have been expecting it to come out like a balloon before. Not so much. It's very subtle, but yes, indeed. Now, the ball does not fit through the ring. As it warms up, I'm going to get in trouble if I leave this like this, because then the ball is going to fit through, and it's going to warm up, expand again, and won't come back out the other side. So I will omit that demonstration for now. Already after a few seconds, it's already fitting a little bit more snugly. So yes, correct, as things cool down. Now, the shrinking was very subtle, but it's exactly the same phenomenon as the loss of elasticity in the rubber, okay? Physically speaking, it's the same thing. It's all about the interaction between the molecules, the stuff that makes up the visible material. okay, and how they behave in relationship to each other. All right, we've seen some fairly ordinary run-of-the-mill materials so far: rubber tube, metal ring, water, fine. I mean, liquid nitrogen. Let's talk about magnets. Magnets are very important here at Cern, okay? They are essential to how we do the physics that we do, and I hope that you've taken the opportunity either before coming here or that you will do after to explore our exhibitions all about the magnets and the systems that are used in Cern to do more advanced physics than what we're playing with here today. But yeah, let's check out some magnets. So, if I... handy-dandy magnets. If I get my... let's do this in order. I have here a magnet, which I can demonstrate to you is a magnet because it'll stick to... where's that? Yes, thank you. Paying attention. Look. I can stick this to this hammer and it does not fall down, okay? Now, all of you are taking that kind of for granted, but that's weird, right? It's just sticking there, okay? But this is a magnet just like you might put a postcard from Geneva on your fridge, okay? Permanent magnet, great. We're going to set it up right here on this little lump of plastic and this mysterious, let's tilt this a tiny bit so you can see better on the camera, this mysterious black disc, not an ice hockey puck, Canada. Ice hockey is this really cool sport, if anyhow. No, you haven't seen it, have you? There you go. Mighty Ducks, there's a whole film of it. Yeah. Well, you're too young to have seen Mighty Ducks. No? There's a whole film about that. Never mind. Wrong sport. Kids, there was this film, a whole series from the 90s, it was amazing. The Mighty Ducks. So I put this magnet down on here and poof, nothing happens. Okay, I can nudge this with my tweezers here, and it just kind of moves around like I would expect it to, because it's just boring, nothing is going on. Okay, fine. So fish that off of there, put our plastic down, get our magnet out, and drop it on there. Cool. But what happens if you cool it down? Liquid nitrogen, 196 below zero. Cool that stuff down. And for the sake of interest, let's just pour some fuel in our train here for later. I'll explain the train setup in a minute. Push that on there, that's looking pretty good. So while this cooks, I feel like I'm on like a cooking show on TV or something. While that's taking care of itself, let's distract you with some other cool stuff. Move time. Fine for time. Tubes. Avast, me hearty. Tubes and another magnet. All right. And for the sake of comparison, a non-magnet. You know it's non-magnetic because there is a handy-dandy little label on it that says non-magnetic. Yeah. Cool. So, let us start with our very exciting plastic tube. Hey! Plastic tube, really? What are you doing? All right, sarcasm. So, we drop one of our spheres through the tube, and it's kind of just going to fall. All right, that took a normal amount of time, right? Wait, why is he talking about how long it takes to fall down? Of course things all fall, they just fall, right? Gravity, we know this. We're not on the moon. The magnet. Big whoop. This was, of course, the control side, okay? But now I have a bit of a challenge, because these boxes are clearly labeled like, these are magnets, these are not magnets. But I have a bit of a problem now, because in that cardboard box where both of those spheres just dropped, they look the same. Now I could just wave the hammer around in there and see which one comes up, would be magnet. But let's see if we can distinguish these things in a different way. Okay? Let's fish them both out. And there's nothing else in there saying this is a magnet, not empty cardboard box, right? Add to the list of very ordinary stuff we've seen in the social file. Copper tube. Copper tube with a convenient gap that we can see through. So we're going to try and work out which one of these is the magnet. All right? I'm going to drop them both in one after the other, and you tell me. All right?
Magnet.
Correct. Because that was weird, right? That took a weirdly long amount of time. Just to, yeah. Oh. Wait. Just, I think, okay. What do we want to bet that I picked the right one up? Whoa. Whoa. I got the magnet. I found the magnet. Okay, that was the magnet. Okay, I got it. Cool. So we identified a magnet. What's going on there? How does that work? So, the difference between the plastic tube and the copper tube is that copper is a conductor. Not that kind of, oh, wait, that one. Right? Copper is a conductor, as opposed to the plastic that isn't, a conductor of electricity. Why am I talking about electricity? We're talking about magnets, two sides of the same coin. These things are closely related. There's an alarm going. That's not the end of the show. We're good. We've got time. And copper is a conductor. And so if we switch out to this next slide, please. On the one hand, with a non-magnetic ball going through the copper tube, gravity just pulls down. Okay? Just gravity doing what it does best. As a side note, in physics, gravity is well understood under the theory of relativity, but it doesn't fit with particle physics. It is a genuinely difficult thing in physics that we have particles and gravity in the same universe, and we just, don't know how it works. Meanwhile, on the magnetic side, we have a magnetic field moving in an environment where it's surrounded by a conductor. A moving magnetic field induces an electric field, and the moving electric field induces an opposite magnetic field. And so that opposite magnetic field slows down the falling of the magnet. And that is what we heard. We really noticed that difference, right? Even over the space of a meter and a half, that's 7 feet. 4-ish. And so they kind of finds an equilibrium, right? Because if the effect was so strong that it stopped the magnet, well then gravity would take over again and keep the magnet falling down, which then induces the electrical field, which induces the magnetic field and slows it down. Okay, so all systems find their own balance. Very good. So magnets are a particular kind of solid, and let's go back to our little cookery show from before. So remember, we had the mysterious hockey puck at the bottom, a layer of plastic, and a magnet on top. And I froze that whole system using liquid nitrogen. And if you remember, when I would poke around with these sets of tweezers, stuff would just kind of move, like normal. But now, back on this guy. Here we go. Oh. Oh. It's looking really well. Makes it sound like it sometimes doesn't work. I can just move this plastic out here and completely remove it, and the magnet stays where it was. It's got a little bit of water ice on it there, but I can just push that off. Oh look, the magnet can spin in place. But I can push this around. And for those of you, that's a really beautiful angle on there actually. If I turn around a bit, might be a bit of a... There we go, we can actually see the gap on camera there, can't we? And just to demonstrate, I've got my little wire here, I can straight up put that through there. 10 years ago, this would get a huge reaction, but people are so blasé about stuff these days. The magnet is flying! Alright, we've got a bigger applause anyway for plastic tubes. It's fine, it's fine. The magnet has no fuse, you can't have it. But so what's going on here, huh? Before, the magnet had its magnetic field, and it was just flowing through our hockey puck, which I can tell you is a superconductor. Alright? Big version. And if you bring up the slide, we can have a look at the little difference here between room temperature, where the magnetic field is just penetrating through our superconductor, and once we've frozen it, and you notice the plastic has gone on that side, the magnetic field becomes, as we say, pinned in place. And to demonstrate this even further, I can actually come and rescue this poor magnet with my hammer, for example, and it jumps up. And actually, I can actually lift the superconductor. And the magnet will eventually get released because it's more strongly attracted to this massive lump of iron on the end of the hammer. But if I were to try and put it back where it came from, that magnetic field, as it turns out, is still pinned in place. You want level 2? Okay, fine. It's pinned in place. So we use effects similar to this. We can do questions at the end. We have effects similar to this in use in the superconductors, in the magnets in the LHC. It's not exactly this effect, but it's related. The fact is, the materials change their properties as a function of temperature. That's what we keep saying throughout this show today. What I was setting up over here is our little train, which is the same setup except upside down. So here, the superconductor is actually inside the train here. Oh, this hasn't worked quite as well as I wanted it to. Let's have a look. This may not work, gang. No, I've been talking for too long, it's warmed back up again. So we'll cool it down, and we'll see if we can get it going at the end of the show. But the point is, the setup here is upside down. So we have the superconductor inside the train. We have a plastic lump in between the train and the track is made of a bunch of magnets. So instead of just having the one field, we have a different shaped field formed by all these magnets. So we'll have a look in a minute at that. So, magnets, a special kind of solid. That's not quite the end of the story, because as spoilers from earlier, you know, the most common type of matter, form of matter in the universe is not solids. Right? You might think, well, planets are solid and they're big, sure. Not all planets are solid, no? Or, you know, there's a lot of water on Earth. Liquids are kind of common, I guess. And then atmosphere seems big, and that's made of gas. So one of those must be the most common. But no, it turns out plasma is the most common substance in the universe, because Earth ain't so special. And we like it, of course, but in the universe, there's mostly kind of nothing, and then stars. And stars are made of a form of plasma as well. So my tech crew are already bringing the lights down a little bit so that we can have a look at some plasma. What? Okay, right, you went to Cern and you saw like a rubber tube and a cardboard box and some magnets like on the fridge, and a kind of special magnet. Let's take a look at some plasma. Ooh. Oh. Wait. Let's switch this baby on. And if the lights come down a little bit more, we should be there. We go. Now that was a coincidence that I was turning this on as the lights came down, right? But here we go. So what have we got here? Our plasma is the blue stuff that's kind of pink as well, right? So we have a gas in here, and in the center of our sphere, we've put a very high voltage, okay? But thankfully, this has a low current. Voltage and current are two different two aspects of electricity, but that means I can touch this with no problem. And as you might notice, where my finger, or even multiple fingers, come to the dark side. Where my fingers touch, the streams tend to accumulate quite dramatically at the top there. And why is that? Well, this effect is what is occurring when that high voltage is causing electrons, which is part of the atoms of the gas, to be stripped off. The word is ionizing. And that means that the electrons kind of want to go somewhere. And the most obvious and easiest place for them to go is the Earth. Okay? In your home electrical circuits, you might have an Earth circuit. Okay? So that when your house gets hit by lightning, safely goes away. And it's the same principle here. Now, the best path for these electrons is to the glass, and then through this flight case into the ground. But when I touch it, the best and the path of least resistance, which is where that phrase comes from, is through this big bag of water called atoms. Okay. So that's all well and good. But let's go for something a bit more visually impressive as well. I can put something between my hand and the plasma ball to see what happens there. We have here a fairly ordinary fluorescent tube, which isn't plugged into the mains electricity at all. But if I were to bring it even closer here, we should get more of an effect. Technique with the cues then, huh? Alright. 12-year-old me. Off goes. And back. It works after a few seconds. But yeah, there we go. So it takes a few seconds each time, because as I've said, these effects are all reversible. So then with the fluorescent tube, the electrons are passing through here, ionizing this gas, okay, and then there's an interior coating there, which then takes that ultraviolet radiation and makes it visible, okay? So again, this is perfectly safe because of the low currents. Don't try this at home. So, I mean, this literal setup, maybe, but yeah. Don't go unplugging lights and try to be like, no. Okay, kids, look after your parents.
Okay.
Promise? So, back to this little train for a second. If we get the lights back up, let's see. Let's have a look. So we had superconductor on top of plastic, on top of magnets, and this time round, if we're lucky, no. Curses. Too long. Alright, well, on that slightly long note, I'm afraid. Everything else. That's our show. Thank you very much. My name's Alex. Enjoy the rest of your day at Cern. And a point about things not working, right? All of the effects you've seen today are real, okay? Front row can testify, okay? Trust the Canadians, trust the Californians. And we do science here at Cern. Sometimes it don't work, and that's okay. All right? I've tried to give you a little example in 45 minutes of all the variety of things we can do, just with varying temperature. But just imagine all of the things there are to discover and learn about by playing with other variables, whether it be in physics, chemistry, biology, social science. Go out there, explore stuff, stay curious. Thank you for visiting, thank you for your attention, thank you for all the interactions, whatever. I'm going to be down here for a few more minutes for any questions, although I would say please stay on the correct side of the barriers. Let's do it over here, because most of you are on this side. And yeah, thank you very much.